Okay, so we're going to have a look at how we do some calculations involving volumetric analysis. So this is using our solution stoichiometry, and then the key thing is finding out which volumes go with which and what we're looking at when we visualize the actual experiment that we're doing. So if we have a look at the first one, we can see here that it says a student was asked to perform a titration to standardize a solution of lithium hydroxide, which is a strong base. So it's telling us that we're doing an analysis on lithium hydroxide. It's telling us the nature of what the analysis is looking for. This is a strong base. It says she placed the lithium hydroxide in a burette and transferred a 20 centimeter cubed aliquot to a hydrochloric acid of concentration 0.1148 moles per decimeter cubed into the titration flask. The reaction was followed with a pH probe, and it was found that 24.25 centimeters cubed of lithium hydroxide was needed to completely neutralize the HCl. So they're not using a indicator at this case, they're actually using a pH probe to determine when the endpoint was. The question wants us to write a balanced equation for the reaction and then calculate the concentration of the lithium hydroxide. So let's have a go. If we have a look, so we said we had lithium hydroxide, so LiOH aqueous, plus hydrochloric acid. And this is going to be our acid-base reaction where lithium hydroxide is our base, HCl is my acid, so the hydroxide is going to pick it up and we're going to get the salt plus water because it's a neutralization reaction. So H2O plus LiCl. So we can see here that this should be balanced and we get a 1:1 relationship. Excuse me. So we know that we've been told we're going to titrate. This is our conical flask. My pen is misbehaving again. So we're going to titrate into our conical flask. My drawing's even worse on this than normal. Got our conical flask. We've got our burette, which is where our lithium hydroxide is. And in here we have the HCl, which is our 20 centimeters cubed of HCl. So we say we're going to titrate, so this means this is my titer volumes, and my aliquot is what's in here because that was delivered from the pipette. So we can see that if we're going to react the lithium hydroxide with the HCl, first things first, we can see that the number of mole of HCl, because I don't have the concentration, is going to be equal to the number of mole of lithium hydroxide. And lithium hydroxide, I do know the concentration of. Oops, sorry, I got that around the wrong way. I know the concentration of my HCl. So in this case, my concentration of HCl is 0.1148. So whatever moles per decimeter cubed. So essentially what's happening is as we drip the lithium hydroxide into this flask, it's going to neutralize. And as soon as we hit the end point, we know that all the HCl that was in this flask is going to have reacted. So if we know that N of HCl is going to equal 20 divided by 1000, which is getting it into decimeters cubed, okay, multiplied by our 0.1148, and that will give us a total of 0.002296 moles. So that's the total number of mole of HCl that's in our flask. Because the number of mole of HCl that reacts is going to be the same as the number of mole of lithium hydroxide, I can now use that as my number of mole of lithium hydroxide. Okay, so now I have a number of mole. I need to know my volume of lithium hydroxide. And if you have a look at the question states that the volume of the lithium hydroxide, okay, is 24.25 centimeters cubed. Okay, so if volume of lithium hydroxide that was delivered from the burette is 24.25 centimeters cubed. So now I can work out my number of the concentration of my lithium hydroxide is equal to mole divided by volume, which is in decimeters cubed. So I'm going to get 0.002296 divided by 24.25 divided by 1,000. Okay, which is going to give me 0.09468. And that will be moles per decimeter cubed. Yeah, so now we can see that we've worked out the concentration of lithium hydroxide by using what we knew reacted from the hydrochloric acid. So this is a little bit different. It's got a dilution in it. So it says a certain toilet cleaner that claims to cling to the bowl and remove rust marks contains hydrochloric acid at a concentration of 3 moles per decimeter cubed. So this is concentration of HCl. And then it wants us to find out the actual concentration of the acid. The analyst diluted 10 centimeters cubed of the product to 250 centimeters cubed in a volumetric flask. So they've had their product they've taken an aliquot of 10 centimeters cubed, diluted into a larger flask up to 250 centimeters cubed. Okay. Then took a 20 ml aliquot of this solution, okay, and then titrated this against sodium carbonate. Okay, and that concentration was 0.0562 moles per decimeter cubed. Okay, so the mean titer, so the volume that came out of the burette was 24.5 centimeters cubed, and they've given us the reaction down here. So I want you to have a go, pause the video and have a go at working this one out, and then I will take you through the calculations to show you how to do it. Okay, so hopefully you had a go. So the first thing that we can do, because we have the volume and the concentration of the sodium carbonate, we can work out our N of Na2CO3, which is going to be 0.056. 0.0562. So this is not 0.0562 multiplied by, again, our volume divided by 1,000 to get it into litres, which is going to give us the mole of sodium carbonate equal to, let's just do this calculation. So it's going to be 1.38 times 10 to the negative 3 moles, so a nice small number of mole. So that was what the amount of sodium carbonate that it took to neutralize what was in the conical flask. Okay, so we've got our sample, then we've got the diluted, then we've got our conical flask that was titrated against. So we've got what was in the burette. Okay, now we can use our mole ratio to find the equivalent of HCl. Okay, and from the equation we can see that N of HCl is going to be equal to 2 over 1 the number of mole of sodium carbonate. So we're going to now take our 1.38 times 10 to the negative 3 and multiply that by 2. So I will get 2.76 times 10 to the negative 3 mole, and that's the number of mole that was in our conical flask here. So if we think about that, okay, this we can work out the concentration that is in here is the same as the concentration that's in here. The number of mole is different because I have more here, but the concentration in this flask is going to be the same as the concentration in that because I've just taken an aliquot into there. So if I work out the concentration of HCl by taking my number of mole and dividing by my volume, which was 10 centimeters cubed for the HCl, 20 centimeters cubed for the HCl, okay, I will find that the concentration is 0.138 molar, or moles per decimeter cubed. Okay, so that's now the concentration in this flask here, which is the same as the concentration in this flask here. And if you remember, we took what was in here, 10 centimeters cubed of that, and multiply and diluted up to our 250 mils. Okay, so what we need to work out here, so I'm going to take my number of mole to work out the overall dilution. So I'm going to take my number of mole, 0.138 moles per decimeter, my concentration. Take my concentration and use my C1V1 equals C2V2. Okay, because now my concentration, I know that I had C1 times 10 milliliters, and C2 is now my 0.138 molar, multiplied by V2, I have 250 milliliters of it. Okay, and so now I can get the C1 is going to be 0.138 times 250, all divided by my 10. Okay, and you can put that into your calculator and work that out. So just this one's a little bit different because it has this dilution step. So once we've worked out the amount from the titration, we need to then step it back. The second part of the question asks us why the analysis would dilute the cleaner rather than use cleaner at the original concentration. If you have a look at this, this has been diluted by a factor of 25, okay, because we can cross out 10 here and cross out 10 here, and it means that it's 25 times more concentrated, which would take 25 times more to titrate, and it already took 25 centimeters cubed for us to reach the neutralization point. So it'd take much longer to be able to titrate that original sample. So what they've done is diluted it in order to make the analysis easier and make the volumes within around a 20-25 mil range is where we usually want for a titration. Okay, we'll look at these calculations again in class. Hopefully it is making a little bit of sense. We're just revisiting our solution stoichiometry.